Tonight, we're going to take a journey through our solar system, but not in the way you might expect. We're not just going to talk about planets and moons. We're going to understand the true scale of our cosmic neighborhood, the actual distances that separate worlds, and the staggering emptiness that dominates everything. Because here's the thing most people don't realize. When you see diagrams of the solar system in textbooks or online, they're lying to you. Not intentionally, but out of necessity. The real distances involved are so immense that if you drew everything to scale, you couldn't fit it on a page, or a poster, or even on a football field. And by the end of tonight, you're going to understand just how much nothing surrounds us, how the emptiness between worlds defines our solar system far more than the worlds themselves, and why this emptiness is both terrifying and beautiful. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now, let's begin. Let's start with what you think you know. You've probably seen countless images of the solar system. 8 planets arranged in a neat line, maybe with the asteroid belt between Mars and Jupiter, all circling a central star that looks about the same size as Jupiter. These pictures are useful for showing what's in our solar system, what objects exist, what order they're in. But they're completely wrong about scale. Devastatingly, fundamentally wrong. If those pictures were accurate, if the planets were really that close together compared to their sizes, everything would be different. Worlds would be pulling on each other with their gravity. Collisions would be common. The night sky from Earth would be filled with giant disks of neighboring planets looming overhead like alien moons, but that's not what we see. When you look up at night, the planets look like bright stars. Even Venus, the brightest and our closest neighbor, appears as just a point of light. Even through small telescopes, the planets are tiny disks, impressive when you realize you're seeing another world, but nothing like the massive spheres you'd expect if the textbook diagrams were accurate. There's a reason for that. The distances between worlds are staggering compared to their sizes. Let's put this in perspective with a simple example that will set the stage for everything else we discuss tonight. If you had a basketball to represent our star and placed it in the center of a room, where would you put Earth? Most people would guess somewhere in the same room, maybe a few meters away, perhaps across the room. The real answer will shock you. Earth would be a tiny ball about 2 millimeters across, roughly the size of a small bead or a peppercorn, and you'd have to place it about 26 meters or 85 feet away. That's the length of about 2 school buses parked end to end, just to represent the distance from our star to Earth. And that's just Earth, the third planet, relatively close to our star. Neptune, the most distant planet, would be about 900 meters or almost 3,000 feet away. That's more than half a mile. You'd need several football stadiums placed end to end to properly show this scale, and most of it would be nothing but empty air representing the void of space. This is the fundamental truth about the solar system that we're going to explore tonight. The objects, the planets and moons, are fascinating and diverse and beautiful, but the emptiness between them is what truly defines the scale. Before we can appreciate the scale of the solar system, we need to start with something familiar. Let's start with Earth, because we need a reference point, something we can actually comprehend from human experience. Our planet measures about 12,742 kilometers, or 7,918 miles across at the equator. That seems large from our perspective. If you wanted to walk around the equator, walking 8 hours a day at a steady pace, it would take you more than a year. If you drove non-stop at highway speed, it would still take about 2 weeks. From our perspective on the surface, Earth feels enormous. There are oceans that stretch beyond the horizon for thousands of kilometers, mountains that take days to climb, continents separated by vast expanses of water. You could spend your entire life traveling and still not see everything. There are remote islands in the Pacific Ocean so isolated that the nearest human settlement is hundreds of kilometers away. There are deserts where you could walk for days without seeing another person. From our ground-level perspective, Earth is incomprehensibly vast. But Earth is just one planet, and compared to some of the other objects in our solar system, it's actually quite small, almost insignificantly small. The closest object to Earth, other than artificial satellites, is the Moon. It circles us at an average distance of about 384,400 kilometers, or 238,855 miles. Let's make that distance more concrete, because raw numbers don't convey the scale. Light travels at about 300,000 kilometers, or 186,000 miles per second, the fastest thing in the universe. Nothing moves faster. That means light from the Moon takes about 1.3 seconds to reach Earth. When you look at the Moon, you're seeing it as it was just over a second ago. The light hitting your eyes left the lunar surface while you were still forming the thought to look up. Astronauts who traveled to the Moon during the Apollo missions between 1969 and 1972 took about 3 days to get there. They traveled in spacecraft, moving at about 11 kilometers, or roughly 7 miles per second relative to Earth. The fastest spacecraft we've ever built, the New Horizons probe that flew past Pluto, would make the trip in about 8 hours. Now, here's something interesting that helps put the Earth-Moon distance in perspective. If you wanted to line up planets between Earth and the Moon, you could fit all 7 other worlds in our solar system in that gap. Mercury, Venus, Mars, Jupiter, Saturn, Uranus, and Neptune. If you placed them side by side, touching each other, would stretch about 390,000 kilometers, or 242,000 miles. That's just slightly more than the distance to the Moon. Think about that for a moment. The space between Earth and our Moon, which seems relatively close in cosmic terms, is wide enough to contain every other planet lined up in a row. That's how much nothing there is, even in this tiny corner of our cosmic neighborhood, and the Moon is right next door compared to everything else we're going to discuss. Now, let's talk about our star, because understanding its size is crucial to grasping the scale of everything else. Everything in the solar system is defined by its relationship to this central object. Our central star is staggering in size. It measures about 1,392,000 kilometers, or 865,000 miles across. That's about 109 times wider than Earth. If Earth were a grape, our star would be a sphere about 2.4 meters, or 8 feet across, roughly the size of those giant inflatable exercise balls. But diameter doesn't tell the whole story. Volume gives you a better sense of the size difference because volume scales with the cube of the radius. About 1,300,000 Earths would fit inside our star. Imagine trying to fill it with Earths, like filling a jar with marbles. You'd need 1,300,000 of them, and there would still be space left over because spheres don't pack perfectly. To put this another way, if our star were hollow, you could fit everything else in the solar system inside it. All 8 planets, all their moons, all the asteroids, all the comets, with room to spare. Our star also contains 99.86% of all the mass in the solar system. Everything else, all 8 planets, all the moons, all the asteroids, all the comets, all the dust and gas floating between worlds, everything together makes up less than 0.2%. This central body dominates not just in size, but in mass, in gravitational influence, in energy output. Every second, it converts about 4 million tons of matter into energy through nuclear fusion in its core. 4 million tons every single second, and it's been doing this for about 4.6 billion years. This energy radiates outward in all directions at the speed of light. The tiny fraction that hits Earth, less than 1/1000th of the total output, is enough to drive our weather, power photosynthesis in plants, evaporate water to create clouds and rain, and warm the surface to temperatures that allow liquid water to exist. Everything on Earth, all life, all weather, all climate, is powered by that tiny fraction of our star's energy. The scale is so large that if you were standing on its surface and looking at the horizon, that horizon would be about 30 times farther away than Earth's horizon is from sea level. The surface area is about 12,000 times greater than Earth's surface area. You could wrap our entire planet's surface around it 12,000 times and still not cover it completely. The temperature at the core reaches about 15 million degrees Celsius, or 27 million degrees Fahrenheit. At the surface, the temperature is about 5,500 degrees Celsius, or 10,000 degrees Fahrenheit, hot enough to vaporize any known material instantly. Now that we understand our star's size, let's look at the planets, starting with the inner solar system. This region contains 4 rocky worlds: Mercury, Venus, Earth, and Mars. These are called terrestrial planets because they have solid surfaces you could theoretically stand on, unlike the giant planets farther out, which are mostly gas and liquid. Mercury orbits closest to our central star at an average distance of about 58 million kilometers, or 36 million miles. We measure distances in the solar system using a unit called an astronomical unit, or AU. 1 AU is the average distance from Earth to our star, about 150 million kilometers, or 93 million miles. So Mercury orbits at about 0.39 AU. This might sound like a reasonable distance, but remember, we're talking about millions of kilometers. Light from our star takes about 3 minutes and 12 seconds to reach Mercury. Mercury is the smallest planet in our solar system, measuring about 4,879 kilometers, or 3,032 miles across. That's about 38% the size of Earth, roughly the size of our moon if you're looking for a familiar comparison. If Earth is a grape, Mercury is a large peppercorn. What's interesting about Mercury is how slowly it rotates. One day on Mercury, the time it takes to spin once on its axis lasts about 58 Earth days, but it completes an orbit around our star quickly, in about 88 Earth days. This creates a strange situation because it rotates slowly while orbiting relatively fast. One solar day on Mercury, from sunrise to sunrise, actually lasts about 176 Earth days. That's 2 Mercury years for every single day-night cycle. If you were standing on Mercury's surface watching the sun, it would creep incredibly slowly across the sky, taking months to move from horizon to horizon. Mercury's surface temperature swings are the most extreme in the solar system. During the day, temperatures can reach 430 degrees Celsius, or 806 degrees Fahrenheit, hot enough to melt lead. At night, they drop to minus 180 degrees Celsius, or minus 292 degrees Fahrenheit, colder than the coldest place on Earth. That's a temperature swing of about 610 degrees Celsius, or 1098 degrees Fahrenheit, between day and night. No other planet experiences anything like this. Venus orbits next at about 0.72 AU, or 108 million kilometers, which equals 67 million miles. Light from our star takes about 6 minutes to reach Venus. Venus is almost identical in size to Earth, measuring about 12,104 kilometers or 7,521 miles across. That's about 95% of Earth's width. Venus is often called Earth's twin because of the similar size and mass, but the similarities end there. The surface conditions on Venus are hellish by any standard. The atmosphere is about 90 times denser than Earth's atmosphere, similar to the pressure you'd experience about 900 meters or 3,000 feet underwater in Earth's oceans. The atmosphere is mostly carbon dioxide, creating a runaway greenhouse effect. Surface temperatures reach about 460 degrees Celsius, or 860 degrees Fahrenheit. That's hotter than Mercury, despite being farther from our star. Hot enough to melt lead, zinc, and some types of glass. The clouds in Venus's atmosphere are made of sulfuric acid droplets, and the atmospheric pressure is so high that carbon dioxide behaves partly like a liquid rather than a gas. Venus also rotates incredibly slowly and in the opposite direction from most other planets. One Venus day lasts about 243 Earth days, but Venus orbits our star in about 225 Earth days. This means a day on Venus is longer than a year on Venus. The sun rises in the west and sets in the east, the opposite of Earth. If you were on Venus's surface, which you couldn't survive without serious protection, you'd experience sunrise about once every 117 Earth days. Earth orbits next at 1 AU, by definition, about 150 million kilometers or 93 million miles. Light from our star takes about 8 minutes and 20 seconds to reach us. This 8-minute light travel time has interesting implications. When you look at the sun, you're seeing it as it was 8 minutes ago. If our star suddenly vanished, we wouldn't know for 8 minutes. The light that left 8 minutes ago would still be traveling toward us. Earth would continue orbiting around nothing for 8 minutes. Then suddenly the light would cut off, and Earth would begin moving in a straight line, no longer held in orbit. Earth measures about 12,742 kilometers, or 7,918 miles across. We've already discussed Earth's size, so let's talk about what makes Earth special in terms of its position. Earth orbits at exactly the right distance for liquid water to exist on its surface. This region around a star is called the habitable zone, or sometimes the Goldilocks zone, because it's not too hot and not too cold, but just right. Venus orbits just inside the inner edge of this zone, and it's too hot for liquid water. Mars orbits near the outer edge, and while it's technically within the habitable zone, it's on the cold side. Earth is right in the sweet spot. But being in the habitable zone isn't enough on its own. Mars is in the habitable zone, and it's not particularly habitable. Earth has several other factors working in its favor. Earth has a large moon, which is unusual for a rocky planet. The moon was probably formed about 4.5 billion years ago, when a Mars-sized object called Theia collided with the early Earth. The debris from this impact eventually coalesced to form the moon. The moon's gravity stabilizes Earth's axial tilt at about 23.5 degrees. Without the moon, Earth's tilt would vary chaotically over millions of years, causing extreme climate swings that might prevent complex life from evolving. The moon also creates tides, which might have played a role in life's transition from ocean to land billions of years ago. Earth also has a magnetic field generated by the motion of molten iron in its core. This magnetic field extends far out into space, creating a protective bubble called the magnetosphere. The magnetosphere deflects most of the solar wind, the stream of charged particles constantly flowing from our star. Without this protection, the solar wind would gradually strip away Earth's atmosphere, the way it did on Mars. Mars orbits next at about 1.52 AU, or 228 million kilometers, which is 142 million miles. Light from our star takes about 12 minutes and 40 seconds to reach Mars. Mars is considerably smaller than Earth, measuring about 6,792 kilometers, or 4,222 miles across. That's about half Earth's diameter, about 53%. In terms of volume, Mars is much smaller. You could fit about 6.5 Mars inside Earth. Mars has two small moons, Phobos and Deimos, both irregularly shaped and probably captured asteroids rather than moons that formed alongside Mars. Phobos is gradually spiraling inward due to tidal forces. In about 50 million years, it will either crash into Mars or be torn apart by Mars's gravity to form a ring system. Mars's atmosphere is very thin, about 1%, the density of Earth's atmosphere. You couldn't breathe it even if it were oxygen, which it isn't. It's mostly carbon dioxide. The thin atmosphere means Mars can't retain heat well. Surface temperatures average about -63 degrees Celsius or -81 degrees Fahrenheit. At the equator during summer, temperatures can reach about 20 degrees Celsius or 68 degrees Fahrenheit during the day, relatively comfortable. But at night, temperatures plunge to -73 degrees Celsius or -99 degrees Fahrenheit. Mars has the largest volcano in the solar system, Olympus Mons, about 22 kilometers or 14 miles high, nearly 3 times the height of Mount Everest. It also has Valles Marineris, a canyon system about 4,000 kilometers or 2,500 miles long, deep enough to dwarf the Grand Canyon. Evidence suggests Mars once had liquid water on its surface, rivers and lakes, and possibly oceans. The water disappeared billions of years ago, lost to space, or locked up as ice underground. Understanding why Mars lost its water is one of the key questions in planetary science. Between Mars and Jupiter lies the asteroid belt, a region containing millions of rocky objects left over from the solar system's formation. The asteroid belt extends from about 2.2 AU to about 3.2 AU, roughly 330 million to 480 million kilometers, or 205 million to 300 million miles from our star. Despite what science fiction suggests, the asteroid belt is not a dense field of rocks that spacecraft must navigate carefully. The total mass of all objects in the asteroid belt is only about 4% of the Moon's mass. If you gathered every asteroid together, you'd have an object smaller than our Moon, maybe about the size of Pluto. The asteroids are spread across such a vast volume of space that if you were in a spacecraft traveling through the belt, you'd probably have to intentionally navigate to see one up close. The average distance between asteroids large enough to see is hundreds of thousands of kilometers. This is why every spacecraft we've sent to the outer solar system has passed through the asteroid belt without incident. Pioneer 10 and 11, Voyager 1 and 2, Galileo, Cassini, New Horizons, all passed through with no special maneuvering required. The belt is so sparse that the chance of a random collision is vanishingly small. The largest object in the asteroid belt is Ceres, measuring about 946 kilometers or 588 miles across. Ceres is large enough that its gravity has pulled it into a spherical shape, and it's now classified as a dwarf planet. The Dawn spacecraft orbited Ceres from 2015 to 2018 and found a world more complex than expected. Ceres has bright spots in some craters that appear to be salt deposits left behind when water ice sublimated. There's evidence of a subsurface ocean, or at least pockets of briny water beneath the surface. Ceres might have geological activity, possibly cryovolcanism, where water mixed with ammonia or salts erupts instead of molten rock. After Ceres, the next largest asteroids are Vesta and Pallas, measuring about 525 and 512 kilometers, or 326 and 318 miles, respectively. Vesta is particularly interesting because it's the only asteroid large enough that you might be able to see with the naked eye under perfect conditions. It's also one of the few asteroids that survived intact from the early solar system. Most asteroids are fragments from collisions, but Vesta is a protoplanet that never quite grew large enough to become a full planet. The Dawn spacecraft also visited Vesta before going to Ceres and found a world with a complex geology. Vesta has a massive impact crater near its south pole, so large that it nearly destroyed the asteroid. The impact excavated material from deep inside Vesta, revealing layers that formed when the asteroid was young and partially molten. Pallas is the third largest asteroid and has a very tilted orbit, inclined about 34 degrees relative to most other asteroids. This high inclination means Pallas regularly crosses through the main asteroid belt at steep angles, leading to high-velocity collisions over billions of years. Pallas's surface is probably heavily cratered as a result. Beyond these three, there are dozens of asteroids larger than 100 kilometers, or 62 miles across, hundreds larger than 10 kilometers or 6 miles, and millions smaller than that. Most asteroids are irregularly shaped chunks of rock and metal, fragments from collisions that happened billions of years ago. They tumble through space, rotating every few hours or days. Some asteroids are contact binaries, two objects that merge together gently in a low-speed collision, creating a peanut or dumbbell shape. Asteroids come in different types based on their composition. C-type asteroids are carbonaceous, dark and rich in carbon compounds. They make up about 75% of known asteroids and are more common in the outer parts of the belt. S-type asteroids are silicaceous, made of silicate minerals and some metal. They make up about 17% of asteroids and are more common in the inner belt. M-type asteroids are metallic, made mostly of iron and nickel. They're relatively rare, but represent the cores of protoplanets that were disrupted by collisions. These are the asteroids that miners might someday target because a single metallic asteroid could contain more platinum, gold, and other rare metals than humans have ever extracted from Earth. Some asteroids have moons of their own. About 16% of asteroids are binary systems, where two objects orbit each other. A few asteroids even have 2 or 3 moons. The asteroid Ida, visited by the Galileo spacecraft in 1993, has a tiny moon called Dactyl, measuring about 1.4 kilometers or less than a mile across. Some asteroids are actually extinct comets. They started as icy objects in the outer solar system, got perturbed into orbits that brought them close to our star, and lost all their ice through repeated heating. What remains is a rocky core that looks like an asteroid but has a comet's origin. There are also Trojan asteroids that don't orbit in the main belt. These orbit at the same distance as Jupiter, but lead or trail Jupiter by about 60 degrees, sitting in stable gravitational points called Lagrange points. There are thousands of Jupiter Trojans, making up a significant population. Mars, Earth, Neptune, and Uranus also have Trojan asteroids, though fewer than Jupiter. The asteroid belt also contains families, groups of asteroids with similar orbits and compositions. These families formed when a larger asteroid was shattered in a collision. The fragments spread out along similar orbits, creating a family that astronomers can identify millions of years after the original collision. The Kirkwood gaps are regions in the asteroid belt with very few asteroids. These gaps occur at orbital distances where an asteroid would complete a certain number of orbits in the same time Jupiter completes a smaller number. For example, an asteroid at 2.5 AU would orbit 3 times for every 1 Jupiter orbit. Over millions of years, the repeated gravitational tugs from Jupiter add up, perturbing the asteroid into a different orbit. This clears out these resonant regions, creating gaps. Asteroids occasionally fall toward the inner solar system, becoming near-Earth asteroids. Some cross Earth's orbit, creating a small but real risk of collision. The asteroid that killed the dinosaurs 66 million years ago was probably about 10 to 15 kilometers, or 6 to 9 miles across. It struck near what is now the Yucatan Peninsula in Mexico, with the energy of about 10 billion Hiroshima bombs. The impact created a crater about 180 kilometers or 112 miles wide, threw dust and debris into the atmosphere that blocked out the sun for months or years. and triggered massive wildfires, tsunamis, and climate changes that killed about 75% of all species on Earth, including all non-avian dinosaurs. Impacts of that size are rare, happening on average every 100 million years or so. Smaller impacts are more common. The Chelyabinsk meteor that exploded over Russia in 2013 was only about 17 meters or 56 feet across. It released energy equivalent to about 30 Hiroshima bombs, shattering windows across a wide area and injuring about 1,500 people, mostly from broken glass. Asteroids a few hundred meters across could devastate a city if they struck in the wrong place. Kilometer-sized asteroids could cause regional destruction. Asteroids 10 kilometers across or larger could cause global devastation. We now monitor the sky for potentially hazardous asteroids. NASA's Near-Earth Object Program tracks asteroids and comets whose orbits bring them close to Earth. We've catalogued most of the kilometer-sized near-Earth asteroids, and we're working on finding the smaller ones. If we detect an asteroid on a collision course with Earth and have enough warning, perhaps decades, we could potentially deflect it. A small change in velocity years before impact could turn a hit into a miss. The DART mission in 2022 successfully demonstrated this by deliberately crashing a spacecraft into a small asteroid moon and changing its orbit. But we need early warning, which is why monitoring programs are so important. Meteorites, pieces of asteroids that fall to Earth, provide scientists with samples of the early solar system. We can study them in laboratories with instruments far more sophisticated than anything we could send to an asteroid. Meteorites have taught us about the age of the solar system, the composition of asteroids, the conditions in the early solar nebula, and the processes that formed planets. Some meteorites, called chondrites, contain chondrules, tiny spheres of rock that formed when droplets of molten material cooled rapidly in the solar nebula. These are among the oldest solid materials in the solar system, forming within the first few million years. Other meteorites are fragments of larger bodies that melted and differentiated, separating into a metal core, rocky mantle, and crusty crust, just like planets do. These give us a window into the internal structure of protoplanets. A few rare meteorites are pieces of the Moon or Mars, blasted into space by asteroid impacts and eventually falling to Earth. We can identify them because the gases trapped in tiny pockets match the atmospheres of those worlds as measured by spacecraft and rovers. The largest meteorite ever found on Earth is the Hoba meteorite in Namibia, weighing about 60 tons. It's mostly iron and nickel and sits where it fell because it's too large to move easily. The impact that created Meteor Crater in Arizona, about 50,000 years ago, involved an object about 50 meters or 164 feet across. The crater is about 1.2 kilometers or 3/4 of a mile wide and 170 meters or 560 feet deep. The impactor was traveling about 12.8 kilometers or 8 miles per second when it struck, releasing energy equivalent to about 10 megatons of TNT. Every day, Earth is bombarded by about 100 tons of dust-sized particles, most of which burn up harmlessly in the atmosphere as meteors or shooting stars. Larger objects, a few meters across, enter the atmosphere a few times per year, but usually break up at high altitude and scatter fragments over a wide area. City-destroying impacts happen on average every few thousand years. Civilization-threatening impacts happen every few million years. Species-ending impacts like the dinosaur killer happen every 100 million years or so on average. Now we reach the outer solar system, where everything changes dramatically. The distances become truly staggering, almost incomprehensible from our human perspective, and the planets are completely different from the rocky worlds of the inner system. These are the giant planets, worlds so large and so different from Earth that they barely seem like planets at all. Before we talk about these outer giants, let's discuss something that fills the space between worlds, something invisible but crucial: the solar wind and the heliosphere. Our star doesn't just emit light and heat. It also emits a continuous stream of charged particles, mostly protons and electrons, called the solar wind. This wind flows outward in all directions from our star at speeds of about 400 to 800 kilometers, or 250 to 500 miles per second. Near Earth, the density of the solar wind is only about 5 particles per cubic centimeter. To put that in perspective, the air you're breathing right now contains about 25 quintillion molecules per cubic centimeter. The solar wind is a far better vacuum than anything we can create in laboratories on Earth. And yet, despite being so thin, the solar wind has profound effects throughout the solar system. As the solar wind flows outward, it carries with it the magnetic field from our star. This creates a magnetic bubble around the solar system called the heliosphere. The heliosphere protects us from most galactic cosmic rays, high-energy particles from exploded stars and other sources beyond the solar system. Without the heliosphere, the radiation environment in the inner solar system would be much harsher. Life on Earth is partly protected by the heliosphere, though Earth's own magnetic field provides most of our immediate protection. The heliosphere extends far beyond the planets, reaching about 120 to 160 AU, depending on the direction. The boundary where the solar wind meets the interstellar medium is called the heliopause. This is where the pressure of the solar wind equals the pressure of the gas and plasma in interstellar space. The shape of the heliosphere is not spherical. Our entire solar system is moving through the galaxy at about 220 kilometers or 137 miles per second relative to the local interstellar medium. This motion creates a bow shock ahead of the heliosphere, like the wake of a boat moving through water. Behind us, the heliosphere is stretched out into a long tail that might extend hundreds of AU. The Voyager spacecraft have given us our only direct measurements of the heliopause. Voyager 1 crossed in August of 2012 at about 122 AU. The spacecraft detected a sudden drop in the density of solar wind particles and an increase in galactic cosmic rays. This confirmed that it had left the heliosphere and entered interstellar space. Voyager 2 crossed in November of 2018 at about 119 AU. Interestingly, both spacecraft crossed at slightly different locations and detected slightly different conditions, teaching us that the heliopause is not a smooth, static boundary but a dynamic, shifting region. Both Voyagers are still operating, still sending back data, though their power sources are gradually failing. The plutonium that powers them decays over time, producing less and less electricity. By the late 2020s or early 2030s, they'll run out of power and go silent forever. But they'll continue coasting through interstellar space essentially forever. In about 40,000 years, Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445, not close by stellar standards, but closer than any star is to us now. In about 300,000 years, Voyager 1 will pass through the Oort cloud of another star system. If that star has an Oort cloud, the Voyagers carry golden records, phonograph records with sounds and images from Earth, greetings in multiple languages, music, and encoded images showing humans and life on our planet. The chance of any alien civilization finding these records is vanishingly small. Space is too vast, the Voyagers too small, and they're not aimed at any particular star. But it was a symbolic gesture, a message in a bottle cast into the cosmic ocean. The solar wind is not constant. Our star goes through an 11-year cycle of activity. At solar maximum, the star's surface is covered with sunspots, and solar flares and coronal mass ejections are common. At solar minimum, the surface is calmer, with few sunspots and fewer eruptions. Solar flares release bursts of electromagnetic radiation across the spectrum from radio waves to X-rays and gamma rays. The most intense flares can disrupt radio communications on Earth, damage satellites, and even pose radiation hazards to astronauts in space. Coronal mass ejections are even more dramatic. These are huge bubbles of plasma and magnetic field that our star ejects into space. When a coronal mass ejection hits Earth, it compresses our planet's magnetosphere and can trigger geomagnetic storms. These storms create beautiful auroras, the northern and southern lights, as charged particles spiral down magnetic field lines and collide with molecules in our upper atmosphere. But geomagnetic storms can also disrupt power grids, damage transformers, and interfere with GPS and radio communications. The largest geomagnetic storm on record, the Carrington event of 1859, caused auroras visible as far south as the Caribbean. Telegraph systems worldwide failed, some caught fire, and operators reported receiving electric shocks. If a similar event happened today, it could cause trillions of dollars in damage to our electricity infrastructure and take years to fully repair. We now monitor the sun constantly with spacecraft like SOHO and SDO, watching for signs of solar flares and coronal mass ejections. When we detect an Earth-directed event, we have a few days of warning before it arrives, enough time to prepare satellites and power grids for the incoming storm. The solar wind also shapes the magnetospheres of other planets. Jupiter has the largest magnetosphere in the solar system, extending millions of kilometers into space. The magnetosphere traps charged particles, creating intense radiation belts far more dangerous than Earth's Van Allen belts. Spacecraft passing through Jupiter's radiation belts must be specially hardened to survive. The Juno spacecraft, currently orbiting Jupiter, uses a titanium vault to protect its electronics. Saturn also has a substantial magnetosphere, though smaller than Jupiter's. Uranus and Neptune have magnetospheres too, though their magnetic fields are strangely tilted and offset from their centers. Mars and Venus have no magnetic fields of their own, so the solar wind interacts directly with their atmospheres. Over billions of years, the solar wind has gradually stripped away much of Mars's atmosphere. Mars used to have a thicker atmosphere billions of years ago, when it also had a magnetic field, but the magnetic field shut down, probably because Mars's core cooled and solidified. Without the protection of a magnetic field, the solar wind has been eroding the atmosphere ever since. Venus has no magnetic field either, but its atmosphere is so thick and massive that the solar wind hasn't been able to remove much of it. The outer atmosphere of Venus is gradually being lost, but at a much slower rate than Mars. Mercury has a weak magnetic field, only about 1% as strong as Earth's. It's enough to create a small magnetosphere that deflects some of the solar wind, but not enough to provide much protection. Mercury's proximity to our star means it's bombarded by an intense solar wind, much denser than what Earth experiences. The solar wind also fills the space between planets with a tenuous plasma. You might think of space as completely empty, a perfect vacuum, but it's not. There are about 5 particles per cubic centimeter near Earth's orbit. That's incredibly sparse by any terrestrial standard. But it's not nothing. Farther from our star, the density drops. Near Jupiter, there might be only about 0.3 particles per cubic centimeter. Near Neptune, even fewer. But there's always something, even in the supposedly empty space between worlds. Dust is also present throughout the solar system. Tiny particles, often from comets, orbit our star just like planets do. When Earth passes through the debris trail of a comet, we see meteor showers as these particles burn up in our atmosphere. The zodiacal light, A faint glow visible in dark skies, after sunset or before sunrise, is sunlight reflecting off this dust. All of this fills the space between worlds, invisible but present, connecting the planets through the common medium of the solar wind and magnetic fields and dust. Jupiter orbits at 5.2 AU, about 778 million kilometers, or 484 million miles. Light from our star takes about 43 minutes to reach Jupiter. To put this in perspective, using our earlier analogy, if our star were a basketball in New York City, Jupiter would be about the size of a large grapefruit positioned somewhere past Denver, Colorado. Jupiter is enormous, the largest planet in our solar system by far. It measures about 143,000 kilometers, or 89,000 miles across at the equator. That's about 11 times wider than Earth. In terms of volume, you could fit about 1,321 Earths inside Jupiter. Jupiter contains more mass than all the other planets combined, more than twice as much. If you added up the mass of every other planet, every moon, every asteroid, every comet except Jupiter, Jupiter would still be more massive. Jupiter is so large that it almost became a star. If it had been about 80 times more massive, its core would have become hot and dense enough for nuclear fusion to begin. It would have ignited and become a second star in our solar system. As it is, Jupiter radiates more heat than it receives from our star. It has an internal heat source, probably left over from its formation and from gravitational compression. Jupiter is a gas giant, meaning it has no solid surface. If you tried to descend into Jupiter, you'd pass through layers of gas that gradually become denser and hotter. Eventually, the pressure would become so high that hydrogen, normally a gas, would behave like a liquid, then like a liquid metal. The core, if there is one, might be a small, rocky or metallic center surrounded by thousands of kilometers of metallic hydrogen. Jupiter's atmosphere is mostly hydrogen and helium with traces of methane, ammonia, water vapor, and other compounds. The visible clouds are organized into bands that circle the planet, created by powerful jet streams moving at hundreds of kilometers per hour. The most famous feature is the Great Red Spot, a storm system larger than Earth that's been raging for at least 350 years. The Great Red Spot is an anticyclonic storm, meaning it rotates counterclockwise in Jupiter's southern hemisphere. Wind speeds around the edge reach about 432 kilometers, or 268 miles per hour. The storm is so large that 3 Earths could fit inside it side by side. Jupiter has at least 95 known moons as of the latest count. The 4 largest, Io, Europa, Ganymede, and Callisto, are called the Galilean moons because Galileo discovered them in 1610. These 4 moons are worlds in their own right, comparable in size to small planets. Ganymede is the largest moon in the solar system, bigger than the planet Mercury. Europa is particularly interesting because beneath its icy surface lies a global ocean of liquid water. This ocean might be twice the volume of all of Earth's oceans combined. Europa is one of the best places in the solar system to search for life beyond Earth. Io is the most volcanically active body in the solar system. Its surface is constantly being reshaped by volcanic eruptions driven by tidal heating from Jupiter's gravity. Saturn orbits at 9.5 AU, about 1.4 billion kilometers or 891 million miles. Light from our star takes about 80 minutes, almost an hour and a half, to reach Saturn. If our star were a basketball in New York, Saturn would be about the size of a large orange somewhere in Nevada, getting close to the west coast. Saturn is the second largest planet, measuring about 120,000 kilometers or 74,600 miles across. That's about 9.4 times wider than Earth. You could fit about 764 Earths inside Saturn. Saturn is also a gas giant with a composition similar to Jupiter, mostly hydrogen and helium with traces of other compounds. Like Jupiter, Saturn has no solid surface, just layers of gas becoming progressively denser and hotter as you descend. Saturn is famous for its magnificent ring system, the most extensive and beautiful in the solar system. The rings extend outward from Saturn for about 282,000 kilometers, or 175,000 miles, more than twice Saturn's diameter. But despite their vast extent, the rings are incredibly thin. In most places, only about 10 to 100 meters, or 30 to 30 feet thick. If you scaled Saturn down to the size of a basketball, the rings would be thinner than a sheet of paper. The rings are made of billions of particles of ice and rock, ranging in size from tiny grains to house-sized boulders. Each particle orbits Saturn independently, held in place by Saturn's gravity. The rings are probably not a permanent feature. They might be relatively young, perhaps only 100 million years old, possibly formed when a moon or comet wandered too close to Saturn and was torn apart by tidal forces. The rings are gradually being pulled into Saturn's atmosphere, raining down as icy particles. In another 100 million years, they might be gone. Saturn has at least 146 known moons, though many of these are tiny objects only a few kilometers across. The largest, Titan, is bigger than the planet Mercury. Titan is the only moon in the solar system with a thick atmosphere, actually denser than Earth's atmosphere. The atmosphere is mostly nitrogen, with traces of methane and other organic compounds. The surface temperature is about -179 degrees Celsius, or -290 degrees Fahrenheit, cold enough that water ice is as hard as rock. Methane and ethane exist as liquids on Titan's surface, forming lakes and rivers in a hydrological cycle similar to water on Earth. Another moon, Enceladus, has geysers of water vapor erupting from cracks in its icy surface. Like Europa, Enceladus probably has a subsurface ocean, making it another candidate for extraterrestrial life. Uranus orbits at 19.2 AU, about 2.9 billion kilometers, or 1.8 billion miles. Light from our star takes about 2 hours and 40 minutes to reach Uranus. If our star were a basketball in New York, Uranus would require you to continue past Los Angeles, out into the Pacific Ocean, several hundred miles from shore. Uranus measures about 51,000 kilometers, or 31,700 miles across. That's about 4 times wider than Earth. You could fit about 63 Earths inside Uranus. Uranus is classified as an ice giant rather than a gas giant. It has a different composition from Jupiter and Saturn, with more water, methane, and ammonia ices, and less hydrogen and helium. The structure is probably a small rocky core, surrounded by a mantle of icy materials and compressed water, overlaid by an atmosphere of hydrogen, helium, and methane. Uranus has a striking blue-green color due to methane in its atmosphere. Methane absorbs red light, so the reflected light appears blue-green. The most unusual thing about Uranus is its axial tilt. Most planets rotate roughly upright relative to their orbital plane. Earth is tilted about 23.5 degrees, which gives us our seasons. Uranus is tilted 98 degrees. It essentially rotates on its side. This means Uranus has the most extreme seasons in the solar system. Each pole experiences 42 years of continuous sunlight, followed by 42 years of continuous darkness. One Uranus year, the time to orbit our star once, is about 84 Earth years. So, if you were born on Uranus's North Pole during summer, you'd experience continuous daylight for your entire childhood and young adulthood. Then, as you reached middle age, the sun would set, and you'd experience continuous night for the rest of your life. No one knows for certain why Uranus is tilted this way. The leading theory is that early in the solar system's history, Uranus was struck by an Earth-sized object in a massive collision that knocked it over on its side. Uranus has at least 27 known moons, all named after characters from Shakespeare and Alexander Pope. The 5 largest are Miranda, Ariel, Umbriel, Titania, and Oberon. Miranda has one of the most bizarre surfaces in the solar system, with enormous cliffs and canyons that suggest it was torn apart and reassembled at some point. Neptune orbits at 30 AU, about 4.5 billion kilometers, or 2.8 billion miles. Light from our star takes about 4 hours and 10 minutes to reach Neptune. If our star were a basketball in New York, Neptune would be somewhere near Hawaii, out in the middle of the Pacific Ocean. Neptune is slightly smaller than Uranus, measuring about 49,500 kilometers, or 30,780 miles across. You could fit about 57 Earths inside Neptune. Neptune is also an ice giant with a composition similar to Uranus. It has a beautiful deep blue color, more vibrant than Uranus's blue-green, also due to methane in the atmosphere. Neptune is the windiest planet in the solar system. Wind speeds in its atmosphere can exceed 2,000 kilometers, or 1,240 miles per hour, faster than the speed of sound on Earth. These winds drive massive storms. When Voyager 2 flew past Neptune in 1989, it observed a storm system called the Great Dark Spot, similar to Jupiter's Great Red Spot, but smaller. When the Hubble Space Telescope observed Neptune a few years later, the Great Dark Spot had disappeared, replaced by a different storm system in a different location. Neptune's storms appear and disappear on timescales of months to years, unlike Jupiter's centuries-long Great Red Spot. Neptune has 14 known moons. The largest, Triton, orbits backwards relative to Neptune's rotation, suggesting it was captured by Neptune's gravity rather than forming alongside the planet. Triton is geologically active, with nitrogen geysers erupting from its surface. It's also slowly spiraling inward toward Neptune. In a few billion years, Neptune's gravity will tear Triton apart, possibly creating a magnificent ring system to rival Saturn's. Now that we've toured all 8 planets, let's step back and truly appreciate the scale. We've talked about sizes and distances, but it's hard to keep all these numbers in your head. Let's use a different way to visualize this that really drives home how far apart everything is. Imagine you're driving across the United States from New York to Los Angeles, a distance of about 4,500 kilometers or 2,800 miles. If our central star was sitting in New York's Times Square, where would the planets be along your route? Mercury would be in Philadelphia, about 140 kilometers or 87 miles away. A short trip, less than 2 hours of driving. Venus would be somewhere around Pittsburgh, about 500 kilometers or 300 miles from New York, about a 5-hour drive. Earth would be near Cleveland, Ohio, about 750 kilometers or 465 miles away. You'd be well into your road trip, probably thinking about stopping for the night. Mars would be in Chicago, about 1,200 kilometers or 745 miles from New York. You've crossed several states by now. Jupiter would be past Denver, about 2,500 kilometers or 1,550 miles away. You've crossed most of the country. Saturn would be somewhere in Nevada, getting close to the west coast, about 4,400 kilometers or 2,730 miles away. Uranus would require you to continue past Los Angeles, out into the Pacific Ocean, about 9,000 kilometers or 5,600 miles from New York. You'd need a boat. Neptune would be somewhere near Hawaii, about 14,000 kilometers or 8,700 miles from New York. You're well out into the Pacific, thousands of miles from any continental shore. This cross-country trip analogy shows you how the distances scale up dramatically as you move outward. The inner solar system, from our star to Mars, fits within about half of the United States. The outer solar system stretches thousands of kilometers beyond, all the way across the Pacific Ocean. And we haven't even reached the edge yet. Here's what all these distances tell us. The solar system is dominated by nothing, by emptiness, by void. If you randomly picked a point somewhere within Neptune's orbit, the overwhelming odds are you'd find yourself in a vacuum. No planets, no moons, no asteroids, nothing but empty space. Even the asteroid belt, which sounds crowded, consists mostly of gaps between objects. If you were in a spacecraft traveling through it, you'd probably have to intentionally navigate to see an asteroid up close. Objects are separated by hundreds of thousands of kilometers. This is hard for our brains to grasp because we live in a world full of things, buildings and trees and cars and people, all packed relatively close together. The farthest you can see on Earth, standing at sea level, is about 5 kilometers to the horizon. Climb a mountain and you might see 50 kilometers. Fly in a plane and you can see a few hundred kilometers. But the solar system operates on a completely different scale. The distances are so immense that even light, traveling at 300,000 kilometers per second, takes hours to cross. Let's think about the solar system in terms of light travel time, because this gives another perspective on the scale. Light from our central star takes about 8 minutes and 20 seconds to reach Earth. By the time you see that bright disk in the sky, you're seeing it as it was 8 minutes ago. The light hitting your eyes has been traveling through space for 8 minutes since it left the star's surface. Light takes about 43 minutes to reach Jupiter. If something dramatic happened on Jupiter right now, a massive storm erupting or a comet impact, we wouldn't see it for 43 minutes. Light takes about 80 minutes to reach Saturn, almost an hour and a half. Light takes about 2 hours and 40 minutes to reach Uranus. Light takes about 4 hours and 10 minutes to reach Neptune. If our star suddenly vanished right now, Earth wouldn't know about it for 8 minutes. For those 8 minutes, we'd continue our orbit around nothing, receiving light that was already on its way. Then suddenly, the light would cut off, the sky would go dark, and Earth would begin moving in a straight line rather than an orbit, flying off into interstellar space. Jupiter wouldn't know for 43 minutes. Saturn wouldn't know for 80 minutes. Neptune wouldn't know for over 4 hours. The implications of these light travel times are profound for space exploration. When we send commands to spacecraft, there's always a delay. The Mars rovers receive commands from Earth that were sent between 4 and 24 minutes earlier, depending on where Mars and Earth are in their orbits. If something goes wrong, if the rover is about to drive off a cliff, it's too late for controllers on Earth to stop it. By the time they see the problem and send a stop command, the rover has already gone over the edge. This is why Mars rovers have some autonomous navigation, the ability to make decisions on their own. When Voyager 2 flew past Neptune in 1989, the spacecraft was over 4 light hours away. Commands sent from Earth took over 4 hours to reach the spacecraft. If something went wrong during the Neptune flyby, mission controllers couldn't react in time. The spacecraft had to be programmed in advance to handle any problems on its own. But Neptune isn't even the edge of the solar system. Far from it. Beyond Neptune lies a vast region of icy objects that extends much, much farther. The first major region is the Kuiper Belt, which begins near Neptune's orbit at about 30 AU and extends to roughly 50 AU, maybe further. The Kuiper Belt is similar to the asteroid belt, but much larger and much farther away. It contains icy bodies left over from the solar system's formation, remnants of the material that never coalesced into planets. Pluto is the most famous object in the Kuiper Belt. Pluto orbits at an average distance of about 39.5 AU, roughly 5.9 billion kilometers or 3.7 billion miles. Light from our star takes about 5.5 hours to reach Pluto. Pluto is relatively small, measuring about 2,377 kilometers or 1,477 miles across. That's about 19% of Earth's diameter. About 170 Plutos could fit inside Earth. From 1930, when it was discovered, until 2006, Pluto was considered the 9th planet. In 2006, the International Astronomical Union created a new classification called dwarf planets. To be a full planet, an object must orbit the Sun, be massive enough for its gravity to pull it into a round shape, and have cleared the neighborhood around its orbit. Pluto meets the first two criteria, but not the third. Its orbit crosses Neptune's, and there are many other objects of similar size in the Kuiper belt. This doesn't make Pluto less interesting. It's still a fascinating world. When the New Horizons spacecraft flew past in 2015, it revealed a geologically complex surface with mountains of water ice, plains of frozen nitrogen, and possible cryovolcanoes. Pluto has 5 known moons, the largest being Charon, which is about half Pluto's size. Pluto and Charon are sometimes called a double dwarf planet because they orbit a point in space between them rather than Charon orbiting around Pluto. There are thousands of known objects in the Kuiper belt, and probably millions more too small or too far away to detect easily. Some are quite large. Eris, discovered in 2005, is roughly the same size as Pluto and more massive. The discovery of Eris is what prompted the reclassification that demoted Pluto from planet status. Makemake and Haumea are other large Kuiper belt objects, each with their own interesting characteristics. But even the Kuiper belt isn't the true edge of our solar system. Beyond it lies something even more vast and more mysterious: the Oort cloud. The Oort cloud is a vast spherical shell of icy objects that surrounds the entire solar system. It's named after Jan Oort, the Dutch astronomer who proposed its existence in 1950. The Oort cloud is thought to begin at about 2000 AU, roughly 0.03 light-years, and extend outward to perhaps 100,000 AU, which is about 1.6 light-years. To put this in perspective, the nearest star to our Sun, Proxima Centauri, is about 4.24 light-years away. The Oort cloud extends almost halfway to the nearest star. The Oort cloud has never been directly observed. No spacecraft has reached it. No telescope has seen objects there. We know it exists because comets occasionally fall inward from this distant realm. These are called long-period comets because they take hundreds or thousands or even millions of years to complete one orbit. When something disturbs an Oort cloud object, perhaps the gravitational influence of a passing star or a massive planet far away, the object's orbit changes. If the change sends it falling toward the inner solar system, it becomes a comet. As it approaches our star, the ice begins to vaporize, creating the characteristic tail. After swinging around our star, the comet either returns to the Oort cloud on a long elliptical orbit or, if it passes close to a planet, it might be ejected from the solar system entirely. Halley's Comet is probably the most famous comet. It orbits our star every 75 to 79 years, last appearing in 1986 and due to return in 2061. But Halley's Comet is actually a short-period comet from the Kuiper belt, not a long-period comet from the Oort cloud. Long-period comets like Hale-Bopp, which appeared in 1997, might take thousands of years to return. The Oort cloud probably contains trillions of objects, possibly more mass than all the planets combined, though spread across an incomprehensibly vast volume. The density is so low that if you were somehow in the Oort cloud, you'd see nothing around you. Objects would be separated by billions of kilometers. You'd be alone in the dark, surrounded by nothing, with our star appearing as just a bright point of light in the distance. The Oort cloud represents the boundary where our star's gravity is barely strong enough to hold objects in orbit. Objects in the outer Oort cloud are so loosely bound that the gravitational influence of passing stars can strip them away. Over billions of years, the Oort cloud is gradually losing objects to interstellar space. Let's now think about the heliosphere, the region of space dominated by our star's solar wind. Our star doesn't just emit light. It also emits a continuous stream of charged particles, mostly protons and electrons, called the solar wind. This wind flows outward in all directions at speeds of about 400 to 800 kilometers, or 250 to 500 miles per second, near Earth. The density of the solar wind is only about 5 particles per cubic centimeter. That's an incredibly thin gas, far less dense than the best vacuum we can create in laboratories on Earth. But over vast distances, this thin flow creates significant effects. As the solar wind flows outward, it creates a bubble called the heliosphere. This bubble extends far beyond the planets. The boundary where the solar wind meets the interstellar medium, the gas and plasma between stars, is called the heliopause. This is effectively the edge of our star's direct influence. The Voyager 1 spacecraft crossed the heliopause in August of 2012, becoming the first human-made object to enter interstellar space. It was about 122 AU at the time, which is about 18 billion kilometers or 11 billion miles. Voyager 2 crossed the heliopause in November of 2018 at about 119 AU. Both spacecraft are still operating, sending back data about the conditions in interstellar space. The signals take over 21 hours to reach Earth, traveling at the speed of light. The heliosphere is not spherical. It's shaped by the motion of the solar system through the galaxy. Our entire solar system is moving at about 220 kilometers or 137 miles per second relative to the local interstellar medium. This creates a bow shock ahead of the heliosphere, like the wake of a boat moving through water, and a tail behind. The heliosphere might extend several hundred AU in the direction we're traveling, and much farther in the opposite direction. So where does the solar system truly end? The answer depends on how you define it. If you define it as the region where our star's solar wind dominates, that's the heliosphere, about 120 to 160 AU, depending on direction. If you define it as the region where objects orbit our star, that's the Oort cloud, extending to perhaps 100,000 AU, or about 1.6 light-years. If you define it as the region where our star's gravity is the dominant influence that extends even further, perhaps to 2 light-years or more. There's no sharp boundary, no edge where you could say definitively that the solar system ends and interstellar space begins. It's a gradual transition. Our star's influence fades slowly over trillions of kilometers until eventually other stars' gravity becomes more important. Let's talk about how the solar system formed, because understanding this helps explain why it's structured the way it is. About 4.6 billion years ago, the region of space where our solar system now exists was a giant cloud of gas and dust. This cloud was mostly hydrogen and helium left over from the Big Bang, with a small percentage of heavier elements created in previous generations of stars that had lived, died, and exploded as supernovae. Something triggered the cloud to collapse. It might have been a shockwave from a nearby supernova, the explosion of a massive star. The shockwave compressed the cloud, and once compression began, gravity took over. As the cloud collapsed, it began to spin faster, like a figure skater pulling in their arms. The spinning caused the cloud to flatten into a disk with a bulge at the center. Most of the material fell toward the center, where it became increasingly dense and hot. Eventually, the center became hot and dense enough for nuclear fusion to begin. And our star was born. But not all the material fell into our central star. The material in the disk began to clump together through a process called accretion. Tiny particles of dust collided and stuck together, forming larger and larger objects. These grew from dust grains to pebbles to boulders to small planets called planetesimals. The planetesimals continued to collide and merge. In the inner solar system, where temperatures were high, only materials that could withstand heat remained solid. These were mostly metals like iron and nickel, and rocky materials called silicates. The lighter, more volatile materials, things like water and methane that turn to gas easily, were vaporized by the heat. This is why the inner planets are small and rocky. In the outer solar system, beyond what's called the frost line, temperatures were cold enough for volatile materials to condense into ice. This meant there was much more solid material available for planet building. The cores of Jupiter, Saturn, Uranus, and Neptune grew large enough that their gravity began attracting the abundant hydrogen and helium gas. Jupiter and Saturn accumulated enormous atmospheres, becoming gas giants. Uranus and Neptune, being farther out where the nebula was less dense, accumulated less gas and more ice, becoming ice giants. This entire process took about 100 million years. By about 4.6 billion years ago, the basic structure was in place. But the solar system wasn't done changing. For the next few 100 million years, the planets' orbits weren't stable. Gravitational interactions caused the giant planets to migrate, moving inward or outward from their original positions. Jupiter probably migrated inward toward our central star, then back outward. Saturn, Uranus, and Neptune migrated outward. This migration had dramatic effects. As the giant planets moved, they scattered smaller objects throughout the solar system. Some were thrown inward, some were ejected from the solar system entirely, and some were thrown into the inner solar system where they bombarded the young terrestrial planets. This period of heavy bombardment lasted until about 3.8 billion years ago. During this time, the inner planets, including Earth, were constantly struck by asteroids and comets. These impacts brought water and organic compounds to Earth, which might have been crucial for the origin of life. The solar system we see today is the result of 4.6 billion years of evolution. It's a dynamic system that's constantly changing, though slowly on human timescales. Planets continue their orbits. Moons orbit planets. Asteroids occasionally collide. Comets fall in from the Oort cloud. Our star continues burning hydrogen, gradually getting hotter and brighter. In about 5 billion years, our star will run out of hydrogen fuel in its core. It will swell into a red giant, expanding to perhaps the orbit of Mars. Earth will be incinerated. Eventually, the star will shed its outer layers, creating a planetary nebula, and the core will collapse into a white dwarf. But that's billions of years away. For now, the solar system continues its ancient dance, each world moving through space according to the laws of gravity and physics. Let's talk about space exploration and what these distances mean for actually visiting other worlds. The farthest humans have ever traveled is the Moon, about 384,000 kilometers, or 239,000 miles. The Apollo astronauts who went there are still the only humans to have left Earth's immediate vicinity. No human has traveled farther than the Moon. The trip to the Moon took about 3 days each way, with the technology of the 1960s and 70s. Modern spacecraft could probably make the trip faster, but not by much. Getting to other planets is much, much harder. The closest planet, Venus, is at minimum about 41 million kilometers or 25 million miles away when Earth and Venus are on the same side of the Sun. At maximum, when they're on opposite sides, Venus is about 261 million kilometers, or 162 million miles away. The distance changes constantly as both planets orbit. A spacecraft to Venus would take several months. The Soviet Union's Venera program sent several landers to Venus between 1961 and 1984. The trip took about 4 months, using the orbital trajectories available with 1960s and 70s technology. The Venera missions were remarkable achievements. Venus's surface conditions are hellish, with temperatures hot enough to melt lead and atmospheric pressure 90 times that of Earth at sea level. Early landers were crushed or overheated within minutes of reaching the surface. But the engineers persevered, designing increasingly robust landers. Venera 7, which landed in 1970, became the first spacecraft to successfully transmit data from the surface of another planet. It survived for about 23 minutes. Later missions lasted longer. Venera 13 held the record for 14 years, surviving 127 minutes on the surface. During that time, it took photographs showing a rocky landscape with flat stones, analyzed the atmosphere and soil composition, and even recorded sound. We have audio recordings of the wind on Venus, captured by a microphone on Venera 14. The Venera landers also found that Venus's surface is primarily basaltic rock, similar to volcanic rocks on Earth, suggesting that Venus once had, or perhaps still has, volcanic activity. Mars is farther but varies even more in distance. At closest approach, Mars is about 54 million kilometers or 34 million miles away. At maximum distance, when Earth and Mars are on opposite sides of the Sun, Mars is about 401 million kilometers or 249 million miles away. This means launch windows to Mars only occur about every 26 months when the planets are favorably aligned. Miss the window and you have to wait over 2 years for the next one. Current technology can get a spacecraft to Mars in about 6 to 9 months, depending on the specific trajectory. There are faster trajectories that take less time but require more fuel. There are slower trajectories that use less fuel but take longer. Mission planners choose based on the spacecraft's capabilities and the mission requirements. Mars has been the target of more missions than any other planet. The first successful Mars flyby was Mariner 4 in 1965, which sent back 22 images showing a cratered, apparently dead world. Early Mars missions changed our view of the planet dramatically. Before spacecraft reached Mars, many people believed it might harbor life, possibly even intelligent life. Percival Lowell had popularized the idea of Martian canals in the late 1800s and early 1900s, claiming to see artificial waterways built by a dying civilization. When Mariner 4's images showed a moon-like cratered surface with no sign of canals or cities, it was a profound disappointment. Later missions revealed a more complex picture. The Viking landers in 1976 were the first successful landings on Mars. Each lander included experiments designed to detect life. The results were ambiguous and controversial. Some tests showed reactions that could indicate biological activity, but most scientists concluded the results were probably caused by unusual chemistry in the Martian soil rather than life. The debate continues to this day. After Viking, there was a long gap in successful Mars missions. The 1980s and early 90s saw several failures. Mars seemed to resist exploration, with spacecraft lost due to technical failures, navigation errors, and bad luck. The Mars Observer mission in 1993 failed just before reaching Mars orbit. Mars 96, a Russian mission, failed at launch. Mars Climate Orbiter in 1999 was lost due to a navigation error caused by a mix-up between metric and imperial units. Mars Polar Lander, also in 1999, crashed on landing, but the successes eventually outnumbered the failures. Mars Pathfinder landed successfully in 1997 with the first Mars rover, Sojourner. Sojourner was small, about the size of a microwave oven, but it demonstrated that rovers could operate on Mars. It drove about 100 meters or 330 feet over nearly 3 months, analyzing rocks and testing rover technology. The real breakthrough came with the Spirit and Opportunity rovers, which landed in January of 2004. These rovers were designed for 90-day missions. They were expected to drive maybe 600 meters or about 2,000 feet, take some photographs, analyze some rocks, and then succumb to dust buildup on their solar panels or mechanical failure. Spirit exceeded its design life by 25 times, operating until 2010, when it got stuck in soft sand. Opportunity exceeded its design life by 60 times, operating until 2018. It drove over 45 kilometers or 28 miles across the Martian surface. Opportunity's longevity was partly due to luck. Several times, when dust buildup on its solar panels threatened to shut it down, Martian dust devils, small whirlwinds, happened to blow past and clean the panels. These cleaning events became known affectionately as cleaning events, gifts from the Martian weather that extended the mission again and again. Both rovers made important discoveries. They found evidence that water once flowed on Mars's surface, not just briefly but persistently. They found minerals that only form in the presence of water. They found layered rocks, showing that some regions were once covered by standing water, perhaps lakes or shallow seas. The Curiosity rover, which landed in 2012, is even more capable. It's about the size of a small car, powered by a plutonium battery rather than solar panels, so it can operate through Martian winter and dust storms. Curiosity has driven over 30 kilometers, or about 19 miles so far, and is still operating. It carries sophisticated instruments to analyze the composition of rocks and search for organic molecules, the carbon-based compounds that are the building blocks of life as we know it. Curiosity has found organic molecules in Martian rocks. This doesn't mean it found life. Organic molecules can form through non-biological processes, but it shows that the ingredients for life are present on Mars. Curiosity also found evidence that Mars once had conditions suitable for life, with liquid water, essential chemical elements, and energy sources. Whether life actually arose on Mars, we don't know. But the conditions were right, at least in some places and times. The Perseverance rover, which landed in February of 2021, is searching for signs of ancient life more directly. It's exploring Jezero Crater, which appears to have once been a lake fed by a river. If life ever existed on Mars, a lake floor with river delta deposits would be an excellent place to look for fossils or chemical traces. Perseverance is also collecting samples that a future mission might return to Earth. Sample return is the holy grail of Mars exploration, because we can analyze samples in Earth laboratories with instruments far more sophisticated than anything we can send to Mars. A Mars sample return mission is planned for the late 2020s or early 2030s. Though the exact timeline is uncertain due to technical and budgetary challenges, Perseverance is also accompanied by Ingenuity, a small helicopter that demonstrated powered flight is possible in Mars's thin atmosphere. Ingenuity was designed for 5 test flights. It's now completed over 70 flights and is still operating, scouting terrain ahead of Perseverance and demonstrating the potential for aerial exploration on Mars. NASA and other space agencies are planning human missions to Mars, though these are still decades away. The challenges are enormous, far beyond anything attempted in human spaceflight so far. A round trip to Mars would take about 2 to 3 years using current propulsion technology. Astronauts would spend 6 to 9 months traveling to Mars in a cramped spacecraft. exposed to cosmic radiation and zero gravity. Then they'd spend several months on Mars's surface, waiting for Earth and Mars to align properly for the return journey. Then another 6 to 9 months traveling back. During the surface stay, they'd work in spacesuits, dealing with the cold, the low pressure, the dust, and the isolation. Then the long trip home. The spacecraft would need to carry enough food, water, and air for the entire journey, or recycle these resources efficiently. It would need to protect astronauts from radiation, which is a serious problem in deep space where Earth's magnetic field doesn't shield you. Solar flares could deliver lethal doses of radiation within hours if astronauts aren't protected. Galactic cosmic rays, high-energy particles from exploded stars, would steadily accumulate damage over months and years. The spacecraft would need robust life support systems that can operate reliably for years without maintenance from Earth. If something breaks, the crew needs to be able to fix it themselves because there's no possibility of resupply or rescue. The psychological challenges would be immense. Astronauts would be confined to a small spacecraft for months, unable to step outside, with communication delays of up to 22 minutes each way, making real-time conversation with Earth impossible. They'd watch Earth become a distant point of light, alone in the void except for their crewmates. Then months on Mars, working long days in difficult conditions, always aware that any serious accident could be fatal because help is months away. Then the long journey home, knowing that Earth is getting closer, but still so far away. The mission would need to carry enough fuel for the return journey, or manufacture fuel on Mars using resources available there. Making fuel on Mars is theoretically possible. Mars's atmosphere is mostly carbon dioxide, and there's water ice beneath the surface. You could use solar or nuclear power to break down carbon dioxide into oxygen and carbon monoxide, extract hydrogen from water ice, and combine them to make methane fuel and oxygen oxidizer. This process has been demonstrated in labs on Earth, but never on Mars. A human Mars mission would probably need to send cargo ships ahead, landing fuel production equipment, habitats, and supplies years before the crew arrives. The crew would arrive to find everything already in place, reducing the mass they need to bring with them. But this requires confidence that the equipment will work reliably for years without human oversight. Despite these challenges, human Mars missions are probably inevitable. Mars is the most accessible planet beyond Earth. It's the only world in the solar system where humans could potentially establish a self-sustaining colony with current or near-future technology. The science return would be enormous. Humans could explore far more territory than robots, make decisions in real time, and handle unexpected situations that would stump autonomous systems. And there's the symbolic importance, the idea that humanity's future isn't confined to one planet. NASA's current plan, the Artemis program, aims to return humans to the Moon by the mid-2020s and use the Moon as a stepping stone to Mars. The idea is to test technologies and procedures on the Moon, where help is only 3 days away, then apply those lessons to Mars. China, the European Space Agency, and Russia also have Mars ambitions, though timelines are uncertain. Some private companies, particularly SpaceX, have announced ambitious Mars plans. SpaceX is developing the Starship rocket specifically for Mars missions. The company's founder has stated goals of establishing a self-sustaining city on Mars within decades. Whether these timelines are realistic is debatable, but the ambition is real. If humans do reach Mars, probably sometime in the 2030s or 2040s, it will be one of the greatest achievements in human history. It will also be a profound demonstration of the scale we've been discussing. The journey will take months, across tens of millions of kilometers. The crew will experience firsthand just how much emptiness separates the worlds of our solar system. They'll watch Earth shrink from a disk to a point of light to just another bright star in the black. They'll experience the isolation that comes from being so far from home that light takes minutes to cross the gap. And if they successfully land, work on Mars, and return home, they'll have proven that humans can cross the gulf between worlds, that the vast distances aren't an absolute barrier. Going to the outer planets is even harder. The fastest spacecraft we've sent to Jupiter took about 13 months to get there. That was New Horizons in 2007, flying past Jupiter on its way to Pluto. New Horizons used a gravity assist at Jupiter, slinging past the giant planet and using Jupiter's gravity to boost its speed for the long journey to Pluto. This technique, called a gravitational slingshot, is essential for missions to the outer solar system. Without it, the fuel requirements would be prohibitive. Pioneer 10 and 11 in the 1970s were the first spacecraft to visit Jupiter and Saturn. They proved that spacecraft could survive the intense radiation around Jupiter. Many scientists worried that the radiation might damage electronics or that there might be debris in Jupiter's environment that could destroy a spacecraft. The pioneers made it through safely, paving the way for later missions. Voyager 1 and 2, launched in 1977, took advantage of a rare alignment of the outer planets that occurs only once every 176 years. This alignment allowed them to visit multiple planets using gravitational slingshots at each one. Voyager 2 visited Jupiter in 1979, Saturn in 1981, Uranus in 1986, and Neptune in 1989. It's the only spacecraft ever to visit Uranus and Neptune. The images and data from the Voyager missions transformed our understanding of the outer solar system. Before Voyager, we knew Jupiter and Saturn were large gas giants with moons, but we had no idea of the diversity and complexity of these systems. Voyager revealed Jupiter's atmosphere in detail, showing the intricate structure of its cloud bands and discovering lightning in the atmosphere. It discovered active volcanoes on Io, the first active volcanoes found anywhere beyond Earth. It found evidence of an ocean beneath Europa's ice. At Saturn, Voyager revealed the rings in incredible detail, showing that they're not solid disks, but made of countless individual particles. It discovered new moons and revealed that Titan, Saturn's largest moon, has a thick atmosphere. At Uranus, Voyager found a bland blue-green world with faint rings and a collection of moons. The images were scientifically valuable, but not visually spectacular. At Neptune, Voyager found a dynamic atmosphere with the fastest winds in the solar system and the Great Dark Spot. It discovered geysers on Triton, making Triton one of the few geologically active worlds in the outer solar system. The Galileo spacecraft orbited Jupiter from 1995 to 2003, making detailed observations over years rather than a brief flyby. Galileo revealed Jupiter's atmosphere and magnetosphere in unprecedented detail. It dropped a probe into Jupiter's atmosphere that transmitted data for about 57 minutes before being crushed by pressure. The probe found that Jupiter's atmosphere is more turbulent than expected, with stronger downdrafts. Galileo also discovered that Ganymede has its own magnetic field, the only moon in the solar system known to have one. The Cassini spacecraft orbited Saturn from 2004 to 2017, revolutionizing our understanding of Saturn and its moons. Cassini's mission lasted 13 years, far longer than originally planned. It discovered new moons and rings, watched seasonal changes in Saturn's atmosphere, and studied the rings in exquisite detail. Cassini's greatest achievement might be its study of Saturn's moons, particularly Titan and Enceladus. The Huygens probe, carried by Cassini and built by the European Space Agency, landed on Titan in January of 2005. It transmitted data for about 90 minutes during descent and 72 minutes after landing. The images showed a landscape with river channels, shorelines, and what appeared to be a floodplain. The probe landed in what might have been a dry lakebed with a thin crust over softer material. Huygens found that Titan's surface is mostly water ice, as hard as rock at those cold temperatures, with a coating of organic compounds. The atmosphere is thick with methane and complex organic chemistry occurring constantly. Titan is the only world in the solar system besides Earth with liquid on its surface, though on Titan the liquid is methane and ethane rather than water. Cassini discovered geysers erupting from Enceladus's south pole, shooting water vapor and ice particles hundreds of kilometers into space. Cassini flew through these plumes multiple times, analyzing their composition. The plumes contain water, salt, and simple organic molecules, suggesting a subsurface ocean in contact with rock, exactly the kind of environment where life might arise. Enceladus is now considered one of the best places in the solar system to search for life. Cassini ended its mission in September of 2017 by deliberately plunging into Saturn's atmosphere. This was done to avoid any possibility of Cassini eventually crashing into Titan or Enceladus and contaminating them with Earth microbes. Even though Cassini was sterilized before launch, there's a tiny chance some hardy microbes survived. By destroying Cassini in Saturn's atmosphere, mission planners ensured it could never contaminate the moons it had studied. The Juno spacecraft has been orbiting Jupiter since 2016, studying Jupiter's interior structure, atmosphere, and magnetosphere. Juno flies in a highly elliptical orbit that takes it from far above Jupiter's poles down to just a few thousand kilometers above the cloud tops. This orbit was chosen to minimize time spent in Jupiter's intense radiation belts while allowing close-up observations during each periapsis pass. Juno has revealed that Jupiter's atmosphere is much deeper and more complex than expected. The cloud bands we see extend thousands of kilometers down. Jupiter might not have a sharp boundary between its atmosphere and interior, just a gradual transition from gas to liquid to metallic liquid hydrogen. Juno has also found that Jupiter's magnetic field is more complex than expected, with regions of different strength and direction. NASA is planning human missions to Mars, though these are still decades away. The challenges are enormous. A round trip to Mars would take about 2 to 3 years. Astronauts would spend 6 to 9 months traveling to Mars, then spend several months on the surface, waiting for Earth and Mars to align properly for the return journey. Then another 6 to 9 months traveling back. The spacecraft would need to carry enough food, water, and air for the entire journey. It would need to protect astronauts from radiation, which is a serious problem in deep space where Earth's magnetic field doesn't protect you. It would need to provide life support systems that can operate reliably for years. And it would need to carry enough fuel for the return journey or manufacture fuel on Mars, which is theoretically possible but has never been done. Getting to the outer planets is even harder. The fastest spacecraft we've sent to Jupiter took about 13 months to get there. That was New Horizons, which flew past Jupiter in 2007 on its way to Pluto. Most Jupiter missions take longer because they need to carry more fuel and instruments, which makes them heavier and slower. The Juno spacecraft, currently orbiting Jupiter, took about 5 years to get there. Saturn is farther. The Cassini spacecraft, which orbited Saturn from 2004 to 2017, took almost 7 years to get there. Uranus and Neptune are so far that we've only visited each once. Voyager 2 flew past Uranus in 1986, 12 years after launch, and past Neptune in 1989, 12 years after launch. The Voyager spacecraft are still the only human-made objects to have visited these distant worlds. There are no current missions to Uranus or Neptune, though planetary scientists would love to send orbiters there. The problem is the distance and the time. A mission to Uranus or Neptune would take over a decade just to get there. By the time it arrived, the scientists who designed it might be retired. The technology on board might be obsolete. And if something goes wrong, the light time delay means controllers on Earth can't fix it remotely. Pluto is even farther. New Horizons took 9.5 years to reach Pluto, flying past in July of 2015. The spacecraft is now headed into the Kuiper Belt and will eventually enter the Oort cloud, though it will run out of power long before it gets that far. The Voyager spacecraft, launched in 1977, are now beyond the heliopause in interstellar space. Voyager 1 is about 160 AU away as of 2025. Voyager 2 is about 135 AU away. They're the most distant human-made objects, and they're still sending back data, though their power sources are failing. By the late 2020s or early 2030s, they'll run out of power and go silent. But they'll continue coasting through space, essentially forever, unless they happen to encounter something. In about 40,000 years. Voyager 1 will pass within about 1.6 light-years of a star called Gliese 445. These missions show humanity's ability to overcome the challenges posed by the solar system's scale. Every mission required years of planning, sophisticated engineering, and precise navigation. Every image, every measurement, every discovery came from teams of dedicated scientists and engineers working to expand our knowledge. But they also show the limits of current technology. We can send robotic probes to other planets, but it takes years or decades. Sending humans is much harder because humans need life support, radiation shielding, and a way to return home. Let's bring this back to Earth for a moment, because understanding how small Earth is in this context makes it all the more remarkable. Earth orbits at exactly the right distance for liquid water to exist on its surface. This region is called the habitable zone because it's not too hot and not too cold. Venus orbits just inside the inner edge of this zone, and it's too hot. Mars orbits near the outer edge, and while it's within the habitable zone technically, it's too small to hold onto a thick atmosphere, so it's too cold. Earth is right in the middle, but being in the habitable zone isn't enough. Mars is in the habitable zone, and it's not habitable. Earth has several other factors working in its favor. Earth has a large moon, which is unusual for a rocky planet. The moon stabilizes Earth's axial tilt. Without the moon, Earth's tilt would vary chaotically over millions of years, causing extreme climate swings that might prevent complex life from evolving. Earth has a magnetic field generated by the motion of molten iron in its core. This magnetic field deflects most of the solar wind. Without this protection, the solar wind would gradually strip away Earth's atmosphere. Earth has plate tectonics, the movement of crustal plates that recycle carbon dioxide and regulate the climate over long time scales. No other planet in the solar system has plate tectonics. Earth has the right mass to hold on to an atmosphere, but not so much mass that the atmosphere becomes too thick. And Earth has water, lots of it, covering about 71% of the surface. All of these factors together make Earth habitable. Change any one of them significantly, and Earth might be lifeless. The fact that we're here, able to study the solar system and understand our place in it, is the result of a long chain of fortunate circumstances. We orbit at the right distance. We have the right size. We have the right atmosphere. We have the right magnetic field. We have the right moon. And we've had billions of years of relatively stable conditions that allowed life to evolve from simple, single-celled organisms to complex multicellular life to intelligent beings capable of building telescopes and spacecraft. In 1990, Voyager 1 took a photograph of Earth from beyond Neptune's orbit, about 6 billion kilometers, or 3.7 billion miles away. Earth appeared as a tiny point of light, just 0.12 pixels across, suspended in a beam of sunlight scattered by the camera. Carl Sagan, the astronomer who suggested taking this photograph, called it the pale blue dot. He wrote, "Look again at that dot. That's here, that's home, that's us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives. The aggregate of our joy and suffering, thousands of confident religions, ideologies, and economic doctrines, every hunter and forager, every hero and coward, every creator and destroyer of civilization, every king and peasant, every young couple in love, every mother and father, hopeful child, inventor and explorer, every teacher of morals, every corrupt politician, every superstar, every supreme leader, every saint and sinner in the history of our species lived there, on a mote of dust suspended in a sunbeam." This image and Sagan's words capture something important about the scale of the solar system. Earth is unimaginably small compared to the distances we've discussed. From any significant distance, our planet simply vanishes. Yet it's the only home we've ever known. Understanding this should give us perspective. The problems that seem overwhelming, the conflicts that dominate the news, the stresses of daily life, they're all happening on this tiny blue dot. In the context of the solar system, let alone the universe, they're microscopic. This doesn't mean our problems aren't real or important. They are. But it does mean that we should keep them in perspective. We're all on this small planet together, circling an ordinary star in an immense solar system. We've covered a lot of ground tonight. From Mercury's scorched surface to Neptune's deep blue clouds, from the inner rocky planets to the distant Oort cloud, we've used analogies and scale models to try to make the distances comprehensible. Now let's think about the future and what comes next in our exploration of these vast distances. What missions are planned? What technologies are being developed? And what might we discover in the decades to come? NASA and other space agencies have ambitious plans for the coming decades. The Artemis program aims to return humans to the moon by the mid-2020s, establishing a sustainable presence with a lunar gateway station in orbit and a base on the surface. The moon will serve as a testing ground for technologies needed for Mars, including life support systems, habitats, resource extraction, and power generation. The lunar environment is harsh, with temperature swings from 120 degrees Celsius or 248 degrees Fahrenheit in sunlight to minus 170 degrees Celsius or minus 274 degrees Fahrenheit in shadow. There's no atmosphere to moderate temperatures or provide protection from meteorites. The lunar surface is covered in fine dust that clings to everything and could damage equipment, and there's radiation from cosmic rays and solar flares that astronauts must be shielded from. But the moon is only 3 days away, close enough that astronauts can return home quickly if something goes wrong. This makes it an ideal testing ground before attempting Mars. Beyond the moon and Mars, there are plans for missions to the outer solar system. The Europa Clipper mission, launching in the mid-2020s, will orbit Jupiter and make multiple close flybys of Europa. The spacecraft will carry instruments to study Europa's ice shell, search for plumes of water vapor erupting from the surface, and analyze the moon's magnetic field to confirm the ocean's existence and determine its salinity. Europa Clipper won't land, but a future mission might. A Europa lander could drill through the ice, though this would be extraordinarily challenging. The ice might be 10 to 15 kilometers or 6 to 9 miles thick. Drilling through that much ice in low gravity with limited power would require technology we haven't developed yet. But if we could reach the ocean beneath, we might find one of the most exciting environments in the solar system, a vast, dark ocean with more water than all of Earth's oceans, possibly rich with dissolved minerals from the rocky seafloor below. If life exists in Europa's ocean, it would probably be similar to life near hydrothermal vents on Earth's seafloor, organisms that get energy from chemical reactions rather than sunlight. The Dragonfly mission will launch in the late 2020s and arrive at Titan in the mid-2030s. Unlike traditional landers or rovers, Dragonfly is a rotorcraft, essentially a large drone. Titan's thick atmosphere and low gravity make flying relatively easy compared to Earth. Dragonfly will fly from location to location across Titan's surface, covering hundreds of kilometers during its mission. It will land at sites of scientific interest, analyze the surface composition, search for organic molecules and potential signs of prebiotic chemistry, and study Titan's methane cycle. Titan is fascinating because it has a chemistry that might be similar to early Earth before life arose. The thick atmosphere contains methane, nitrogen, and complex organic molecules constantly forming through photochemistry driven by sunlight. These molecules rain down onto the surface, accumulating over millions of years. If we can understand the chemistry happening on Titan, we might gain insights into how life could have originated on Earth billions of years ago. There are also proposals for missions to Uranus and Neptune, though these haven't been funded yet. Planetary scientists have advocated for orbiters to these distant ice giants for years. We've only visited each once with brief flybys. We know almost nothing about their interiors, atmospheric circulation, magnetic fields, or the detailed characteristics of their moons. A Uranus orbiter could study the planet's bizarre tilted rotation, investigate why its magnetic field is so offset from its center, and explore its moons in detail. Miranda, one of Uranus's moons, has one of the strangest surfaces in the solar system, with enormous cliffs and canyons, suggesting it was disrupted and reassembled at some point. A Neptune orbiter could study the planet's powerful winds and dynamic atmosphere, investigate its magnetic field, and study Triton in detail. Triton is one of the most intriguing moons, with active nitrogen geysers and a surface suggesting recent geological activity. Triton is also slowly spiraling inward, doomed to eventual destruction when Neptune's tidal forces tear it apart in a few billion years. The challenge with missions to Uranus and Neptune is the distance and travel time. Even using gravitational assists at Jupiter or Saturn, it takes over a decade to reach these worlds. By the time a mission arrives, the spacecraft's designers and builders might be retired. The technology on board might be obsolete, by modern standards, though still functional. This requires a different kind of thinking about space missions, planning for the very long term. The search for life beyond Earth is a major driver of solar system exploration. We've talked about Europa and Enceladus with their subsurface oceans. We've talked about Titan with its organic chemistry. Mars is also a candidate, though any life there is probably microbial and possibly extinct. But there are other possibilities. Venus, despite its hellish surface, might have habitable conditions in its upper atmosphere. About 50 to 60 kilometers, or 30 to 37 miles above the surface. Venus's atmosphere has Earth-like temperatures and pressures. Clouds of sulfuric acid droplets exist at that altitude, which sounds hostile. But some Earth microbes can survive sulfuric acid, and the clouds might have water dissolved in them. Recent detections of phosphine in Venus's atmosphere, though controversial and still debated, raise the possibility of microbial life floating in the clouds. The detection hasn't been confirmed and might be a measurement error or unusual chemistry, but it sparked renewed interest in Venus. There are now proposals for missions to study Venus's atmosphere in detail, possibly even deploying balloons or airships that could float in the habitable zone for days or weeks. Ceres, the dwarf planet in the asteroid belt, also has potential. The Dawn spacecraft found evidence of a subsurface ocean or at least large pockets of briny water. Where there's liquid water and energy, there's potential for life. Beyond exploring individual worlds, there's also the question of understanding the solar system as a whole, how it formed, how it evolved, and how it compares to other planetary systems. We now know that planets are common around other stars. As of 2025, we've confirmed over 5,000 exoplanets orbiting other stars, with thousands more candidates awaiting confirmation. These exoplanets show incredible diversity. There are hot Jupiters, giant planets orbiting very close to their stars with orbital periods of just days. There are super-Earths, rocky planets larger than Earth but smaller than Neptune, a type we don't have in our solar system. There are planets orbiting in the habitable zones of their stars where liquid water could exist. And there are bizarre systems unlike anything we expected, planets with eccentric orbits, multiple planets in resonant orbits, planets orbiting binary stars. Studying our own solar system helps us understand these exoplanet systems. We can test theories of planet formation and evolution against the detailed observations we can make in our own neighborhood. And conversely, seeing the diversity of exoplanet systems helps us understand that our solar system is just one possible outcome. There's no single normal planetary system. Every system is unique, formed from different initial conditions and shaped by different evolutionary paths. Looking farther into the future, there's the possibility of human settlements beyond Earth. Not just visiting other worlds, but actually living there permanently. Mars is the most obvious candidate for a human settlement in the near term. It has resources that could be used to support a colony, including water ice, carbon dioxide for making fuel, and minerals for construction. The day-night cycle is similar to Earth's, about 24.5 hours. The gravity is about 38% of Earth's low, but possibly enough for long-term health, we don't know for certain. A Mars settlement would need to be mostly underground or heavily shielded to protect inhabitants from radiation. It would need greenhouses for growing food, probably also underground with artificial lighting. It would need life support systems to recycle air and water with very high efficiency. And it would need to be largely self-sufficient because resupply from Earth would take months and be enormously expensive. The first Mars settlement might be a research outpost, like Antarctic research stations on Earth. Scientists and engineers would live there for tours of duty, perhaps a year or two at a time, before returning to Earth. But eventually, if the settlement grows large enough and becomes self-sufficient enough, people might choose to stay permanently. Children might be born there, the first humans, who are not from Earth. These Mars-born humans would be physiologically adapted to Martian gravity. They might never be able to return to Earth because Earth's higher gravity would be too much for their hearts and bones. The Moon is another possibility for a settlement, closer to Earth and possibly more practical as a first step. A lunar base could serve as a shipyard for constructing spacecraft, taking advantage of the Moon's low gravity to launch vehicles using less fuel. The Moon has water ice in permanently shadowed craters near the poles. This ice could be extracted and split into hydrogen and oxygen, providing both life support and rocket fuel. All of this is speculative, decades or centuries in the future. But the fundamental limitation isn't technology or resources. It's distance. Every ambitious plan for space colonization must contend with the vast gulfs between worlds. Travel times measured in months or years. Communication delays measured in minutes or hours. The impossibility of quick resupply or rescue. Understanding the true scale of the solar system isn't just an abstract exercise. It's fundamental to understanding what's possible and what's not, what we can achieve and what will always remain difficult. We've developed technologies that allow us to cross these distances slowly and at great expense, but we can do it. Every spacecraft that reaches another world proves that the distances aren't absolute barriers, And as technology improves, as propulsion systems become more efficient, as we learn to use resources found in space rather than bringing everything from Earth, these distances will become less daunting. Perhaps in a century or two, travel between Earth and Mars will be routine, no more remarkable than transcontinental flights are today. Perhaps humans will live and work throughout the solar system, on the Moon, on Mars, in the asteroid belt, in orbit around Jupiter's moons. Perhaps we'll look back on this era as the beginning of humanity's expansion into space. Or perhaps the distances will always remain a barrier. Perhaps we'll always be confined to Earth with only robotic probes venturing to other worlds. The future is uncertain. But what's certain is this: the solar system is vast, far vaster than most people realize. The distances between worlds are immense, almost incomprehensibly so. And yet, despite these distances, we've managed to visit every planet, to see these distant worlds with our own eyes through the cameras on our spacecraft. We've measured the solar system. We've crossed it, at least with our machines. We've studied it and begun to understand it. And we're planning to explore it further, pushing the boundaries of what's possible. The key takeaway is this: the solar system is far larger than most people realize. The distances between planets are staggering compared to the sizes of the planets themselves. The gaps, the emptiness, the void, dominates everything. If you took all the planets and moons and asteroids and comets, everything solid in the solar system, and gathered them together, you'd still have a collection of objects smaller than our star, and the space they'd leave behind would be vast beyond comprehension. The solar system is mostly nothing, but within these immense distances, there are fascinating worlds. Gas giants, with storms larger than Earth. Ice giants tilted on their sides, with the strangest seasons imaginable. Moons with buried oceans that might harbor life. Rings made of billions of chunks of ice orbiting at incredible speeds. Volcanoes that dwarf anything on Earth. Canyons that could span continents. And in the midst of all this, there's Earth. One small rocky planet, orbiting at just the right distance, with just the right size and composition, and magnetic field and moon to make it habitable. Understanding the scale of the solar system gives us perspective. It shows us how small we are. It shows us how isolated we are. It shows us how precious our home planet is. It shows us that space exploration is difficult and takes time, that the distances are so vast that even light takes hours to cross from our star to the outer planets. But it's worth doing because every mission expands our knowledge and our perspective on our place in the universe. The next time someone asks you how far apart the planets are, you can tell them. You can describe the true scale, how distances between worlds measure in hundreds of millions of kilometers. You can explain that light itself takes hours to cross from our star to the outer planets. You can talk about how the emptiness defines the solar system far more than the planets themselves. And maybe, just maybe, that understanding will give them the same sense of wonder and awe that comes from truly grasping the scale. The wonder of knowing that we live in a cosmic neighborhood so immense that light takes hours to cross it, yet so precisely arranged that our small planet can sustain life. The wonder of knowing that for all the vast distances, we've managed to send spacecraft to every planet, to land on Mars, to orbit Saturn, to fly past Pluto. The wonder of knowing that despite being so small and so isolated, we're capable of understanding our place in this immense system. Thank you for joining me on this journey across billions of kilometers and billions of years. If you found this exploration valuable, please consider liking this video and subscribing to the channel. It helps me continue making these deep dives into space and science. And remember, we live on a small planet in an immense solar system, but it's our planet in our solar system, and it's full of wonders waiting to be explored.